Thank you. Okay, it works. Alrighty, let's get into it. I'll start the talk with a little anecdote, and then I'll introduce myself. It's a bit weird, but let's do that. So yeah, a short anecdote. Just wanted to kind of like showcase why profilers are important. I mean, I think quite a few people think that they are important tools. But in case you haven't used one or you're not really aware what they do, I just wanted to showcase in what kind of situation they may be useful. I was making some open source contribution to a Rust library, and just like for fun. And it was like a very small change, which I have there at the bottom right. And it was, like I was changing essentially, uh, it was slightly more big than that, but the summary of the change was essentially changing some print statements to print just hi and print wrapper of hi, essentially. And you'd expect that this would not have such a big performance impact, but it actually made some of the benchmarks of the open source library I was contributing to 50% slower, which was quite a surprise. Um, I didn't. Also, like one thing that made this slightly harder to figure out was that these print statements were not written in the code, but they were actually generated by some proc macros, essentially. So it was slightly harder to track down, but I didn't know what was going on. Like I was like, okay, this is a very small change. Why would it get 50% slower? And I use a profiler. In this case, I use Samply, which is a native profiler, which is actually really good, and it's also written in Rust, but it's for native code. Love it. And I saw that like there was a big difference in between the profiles of before the change and after the change. And after the change, there were like all these allocations that were happening, and I really couldn't figure out. Like that was a good end though. And then after figuring out that there was an additional allocations happening, then actually I figured out one thing, that the Rust compiler cannot optimize out. Essentially, like the Rust compiler can optimize out the first line. It figures out that hi is essentially a static, and it can just put it in the first string, essentially. But when you wrap hi on with anything, it cannot do that optimization anymore. And the fix was just to get rid of the wrapper in the procmago generated code when we know that it's a static. So I think this is a very good example. It was a small change, but I would have not. I never guessed that there was an additional allocation happening because it was also like the compiler, optimizing out something, and it was not doing that anymore. So I really enjoy using profilers, and I do that quite a bit at my day job. So we can talk a little bit about that. I'm a senior engineer at Shopify, and essentially what I work on is Shopify has this templating language that is called Liquid, and it's similar to Jinja or ERB. So it's just a templating language, essentially, and it allows you to define what your storefront looks like. So you can do things like, for every product in your collection, print this HTML to the customer. And what I work on is actually we're trying to take Liquid and compile it into WebAssembly. And it's mostly a performance-sensitive project, so we do spend quite a bit of time trying to figure out where time is spent. And yeah, I have a bunch of interests. You can talk about, with me about compilers, profilers. I'm also somehow involved with a bunch of distributed systems because, as you can imagine, these storefronts have to be rendered across the world, the closest to the customer as possible. And so it's all part of one big mission to make this fast. And it's both CPU work and I/O and trying to distribute the data around the world. I'm from Sicily, and I love beach volley. Also climbing a little bit and video games, which I guess pretty stereotypical. Okay. um, I I built a provider for WebAssembly, and this is kind of like a talk about what I did, how it works, and what I learned, and some of the things I wish maybe we could do as a community to further improve the state of profiling for WebAssembly. So the reason why I built this profiler specifically was that someone, I think, pointed out that currently we do offer the ability for third-party developers to profile their Liquid code. And this is just uses some instrumentation because Liquid current, like the previous version, is an interpreter. So you can just add a bunch of instrumentation to the code while it's interpreted to then collect information about how time is spent in your theme when it renders. But now that we compile the WebAssembly, it becomes slightly harder, and I was wondering if there would be an easy way, because we compile to something closer to native, to just use a proper profiler rather than having to instrument the code. And that's why I built this. So following on that, I'm going to try to explain a little bit what a profiler is and usually how it works internally. So there's kind of like two types of profilers. Sampling, which is what I'm going to talk about today, and instrumenting or tracing, which is another kind of compilers. They are also very good, but what they kind of like need you to do is instrument or automatically instrument your code, and they usually have a little bit of overhead because essentially, for example, for every time you enter a function, you need to increase a counter that you've entered that function, and so that you know where time is spent. Sampling profilers don't need you to do that kind of instrumentation, and they're usually considered to be low overhead, and also, you know, it's also like I was trying to make one, and I was just mostly trying to learn, and I could take quite a bit of inspiration from other sampling profilers, like for example, I don't know how to pronounce it, but Prof RS is one that I took quite a lot of inspiration from. And yeah, I just built a sampling one. So I'm going to mostly talk about how sampling profilers work today. Cool. So I like to think a bit about sampling profilers, and maybe this is a metaphor that only works for me, but hopefully it works for someone else in this room. But it's a bit like a movie to an extent, and you know, like bear with me with the metaphor. But what a movie is just like a collection of pictures, right? And essentially, if you put them one after the other quickly enough, you get a movie, right? Like you get essentially. You can understand movement in that sense and the dynamics of the system, right? A picture on its own is limited, but a movie has additional information because it's an aggregation of them. And sampling providers are maybe similar, if you allow me to keep on going on this weird analogy. But essentially, you take a snapshot of your program at a certain interval, and essentially, the more snapshots you take, the more precise the information you get out. But if you do it enough times while the program runs, you're going to get a sense of what's happening in the program, right? You know that you were in main, that called foo, that called bar, right, at a certain sample. And then the more samples you take, you may see essentially the functions that appear the most in each sample are usually where you spend time. And so you put together informations from snapshots, and you get profile data out of that. But we'll go back to this with more examples later on. Okay, this is kind of like an introduction to this, but like, can we, how do we actually create one such profiler? So one thing I need to mention here is that the talk is about building a profiler for WebAssembly, but maybe I should have been slightly more specific. But I had to use a specific runtime because WebAssembly has to run somewhere. Like there is no, so far, CPU that actually can take WebAssembly and run it on bare metal, right? And so you have to use one engine that can take your WebAssembly and then actually run it on the machine you have at your disposal, right? And so I used wasmtime. Why? It's like a pretty, I'd say like it's a pretty good engine. Um, it's pretty fast. It's built in Rust, and also it has a few APIs that make building a profiler easier. Also, I work, as I said, at Shopify. We have few people that contribute directly to wasmtime. So if I needed anything, I could just go to them and ask them, how can I do this? Or can we add an API? Or can we slightly change one? And so it was slightly easier because of that too. So that's one thing. Also, wasmtime actually nowadays has its own profiler that it's embedded in wasmtime itself. When when I did the work, it was not the case, but now there is one, and that's great. Cool. So as I said before, right, like we want to take these snapshots at every single point in time, whenever, like with enough time in between, because we don't want to stop the program all the time. But we need some way of essentially stopping the program, taking a snapshot, and then making it continue do its thing, right? And so usually when you, like on the left side, I'm not great at drawing or diagramming, but I'll try my best to explain what I'm trying to convey with this slide, essentially. But you have the runtime, which is wasmtime, right? And you give it essentially a program, and when you just use wasmtime, like I guess like with no flags, no specific configuration, what happens is essentially wasmtime takes your wasm, it compiles it to assembly, and then it just runs the assembly till it's done. There is no way to get back control to the host or the runtime, essentially. And I guess this is good to an extent. Like you're gonna, usually in most cases, you want essentially your runtime to just run your code and do it as quickly as possible. So that's kind of what it does. But as I said, we need to have a way to kind of like stop the program every so often and take back control, essentially, get out of the program itself and collect some information about the program, right? And so in order to do so, we can use epochs. Epochs are a feature in wasmtime, which allow the code, essentially, like what wasmtime does is when it generates the assembly, every so often in the assembly, it adds some instruction to check if an epoch has been reached. And if the epoch has been reached, it gets out of your program and goes back into the host code, essentially, like the code that you've written, essentially. And so you get back control to the runtime, essentially. And this is good because if we get back control, then we can use other wasmtime APIs to get information about the program running, and that's our sample. That's a sampling profiler, essentially. Cool. So we have one mechanism to at least stop the program execution every so often when this epoch is reached. And then we can do whatever we want. We can collect the sample that we need. But how do we, so like wasmtime allows you, essentially, it generates code that stops every so often, checks the epochs. But like if nothing increases the epoch counter, then the program is just going to run forever, essentially, because the epoch has not reached, so it can just keep on going, and it will never yield back control to the runtime. And this is one very common way to do this, is to use set itimer, which is, I don't know if it's POSIX or Unix, but like Linux and Mac OS expose essentially this system call, which essentially you tell your operative system to send a signal every so often, so like some cadence that you specify. And then you can install a signal handler, like what happens when the OS sends you this signal. And one thing that we can do is, okay, now we have something at least that has some sort of like, I guess, stops the program or like at least sends a signal every so often. So we have what we need to then actually increase the epoch counter. So like what happens is the OS stops the entire program with a signal, and we do something very minimal, which is just increase the epoch counter when this happens. And then when the program restarts, right, after the signal is handled, it's probably inside wasm, like the wasm execution, which then is going to check the epoch counter. Now it's been increased, and it stops and yields back control to the runtime. Cool. Also, like after the work, actually, I had to make this work on Windows as well, and for that, I just use a thread, which is better than nothing. So I have another thread that just sends, essentially increases the epoch counter every so often. So that's one thing. And then what do? We use actually like wasmtime already allows you when you are in when you're handling an epoch, or really like when you're handling any call from wasm into the host, like the runtime itself, it allows you to capture a stack trace. So that was one of those APIs together with epoch handling that was nice to have in wasmtime that would make it easy to build such a profiler. And so what we do is we ask wasmtime, okay, what's the current stack trace or back trace, call stack, whatever, like there's like multiple names for these things, but essentially, what are the functions that are currently active on the stack for the wasm program? And essentially, wasmtime is gonna give us back something like, your, like it's main, foo, bar, bus, right? Like the stack, the call stack, backtrace, whatever you wanna call it. And so every time we do that, like every time we get an epoch interruption, we capture one such sample. And if we do it fast enough and enough times, essentially we've built enough information to have profiling data that then we can feed a UI to then display flame graphs or other kind of profiling visualizations. And to be clear, I did not build one such UI because there is like enough there that you can just use if you give them something like a file with the information about the program and the profile data. And what the profile data kind of looks like is this. So you have frames, which is all the functions you've ever seen. Essentially, like like main, foo, bar, all the functions of your program are like, it's almost like a set, essentially. And it's all the functions that have ever been seen in all the samples you've taken. So such that we don't duplicate those names in all the samples, essentially. And then you have samples, which is a vector of usize. And so this is a bit of indirection, but essentially the usize is just index into the frames so that the names are not duplicated, right? Like you don't want to have main in the samples like, I don't know, 1,000,000 times. That's like a waste of space, essentially. And so you can kind of optimize this out with, you have frames that are all the unique names, and then samples, which is just a vector of vectors of function names. So the inside vector is just one sample, essentially. It's like all the function names in that sample, and then the outside vector is just all the samples you've taken. And then you can have weights, which is an optional of a vector of U128. And so like each sample can have its own weight, essentially, like how important it was. Usually you use time as the weight, essentially the time that has elapsed since the last sample you've taken. That's the importance of that specific sample. But you can use also other other metrics actually. And one that was actually quite useful because this ended up being used to an extent inside Shopify because we offer some sort of like function as a service system where you can customize some of the behavior of your storefront, for example, your checkout or your cart, maybe like delivery options and all of that. And we do this through essentially third-party developers can submit WebAssembly functions to us, but one limitation that we impose is that these WebAssembly functions cannot exceed a certain computational budget, and this is done through wasmtime. Wasmtimes allows you to essentially limit the amount of computations that one invocation to a WebAssembly program can do, and this is through Fuel. It's another API that comes from wasmtime, but essentially you can think of it as anytime you do any operation, you burn some fuel. And when you've burned all the fuel that you were given, the execution stops. And that's it, like you cannot compute farther than that. And this is so that, we don't want people to write functions that increase the checkout time by like 10 seconds. That would be insane and also probably decrease conversions for us and our customers. And so we have a very strong limit on how much computations you can do on these functions, and this is Fuel. And so one thing that we ended up adding to this profiler is not only we can weight these samples by time, but we can also weight it by this fuel that has been consumed since the last sample has been taken. And that turned out to be quite useful even internally because it helped people kind of figure out where they were spending their fuel. And this is a little bit of looking ahead. It's mostly just like dreams or wishes or hopes I have for maybe better profilers for the future. And there's like mainly two topics that I kind of care about that I wish I could see happen in the future. And so it's two things. One is supporting languages runtimes profiling inside of WebAssembly. And the other one is more easily allow new languages, like entirely new languages, that are built on top of WebAssembly to essentially emit enough information such that profilers can actually understand the semantics of the language, not of the assembly that they produce. And so I'm going to go into more details on each of them. So the first thing is, right, you can compile your Rust or your C to WebAssembly. And if you run one profiler like mine or even the one that is now included in wasmtime, you would see enough information to figure out essentially what's happening in your program, because these are languages that are compiled to native code, and native code here is WebAssembly. And so if you're calling the Rust function food, you would see it in your, maybe it's mangled, but you can unmangle that, demangle that. You would see it in your profiles, like in your samples, essentially. But WebAssembly is a very large boat, essentially. And there's like use cases where you may want to run your JavaScript or your Ruby or your Python inside of WebAssembly runtimes. Maybe because you want to run them in the browser for whatever reason that is, or you want to offer again something similar to what we do right at Shopify, where we allow people to write their own customizations, and sometimes they don't want to write. These third-party developers don't want to write Rust or C because they're used to writing JavaScript or Ruby, and so you're gonna have to make them mapping. And you can run, Ruby and JavaScript and Python in WebAssembly, so there is no particular issue there. But if you try to profile them using a profiler that works with WebAssembly, like the wasmtime one or the one I wrote, you wouldn't get any information out of that, because it's something similar to when you try to profile, a Ruby a Ruby program using perf or a native profiler, right? You would only see, oh yeah, you're using the Ruby VM because that's the C code that actually runs on your machine, but you don't actually understand like what Ruby code is the VM running. Who knows, right? Like there is no information there, and so like there may be like a solution here, especially because it's a fairly new platform, WebAssembly, and there is ways to define. We have ways to define interfaces like WASI, and with components, it's going to be even easier, right? Maybe we could define a shared interface that all of these runtimes can expose to essentially inform the profiler, oh yeah, like, okay, yes, that C code or Rust code is running that powers the VM itself, but also like at this specific point in time, this Ruby code or this JavaScript code was actually running inside the VM. And with that, we could collect both samples and maybe even interleave them with some heuristics or whatever, just keep them separate, but at least there you can put them on a like on a time graph together and figure out what's happening maybe. But at least we have information about what's happening inside. So that's one thing that I wish actually existed. The other thing is, and this maybe it's just because, as I said, like this is kind of like what I do. So we are writing a compiler for Liquid. And Liquid is our own language, right? It's a simple language. It's a templating language. It's not doesn't have that much, semantics or complexity. But we compile it to WebAssembly itself. And sure, we could have used LLVM to do that, but it felt like a bit of a overkill to compile a templating language to WebAssembly to use LLVM. Also, ideally, we want to run this possibly during a request, so running all of LLVM may take a little bit of time, and it may essentially it may not be worth it. And so the other side of this is, so you don't want to use LLVM. You can use a bunch of WASM code generators that are like very fast, and they exist in Rust and also other languages, right? The issue there is though that none of these, as far as I know, and maybe this has changed or I haven't looked too hard. Essentially, they don't emit any kind of debug information like dwarf for your WebAssembly, right? Like, so I'm compiling Liquid in my case, right, to WebAssembly. Now I have this WebAssembly, I run it in an engine, and I can profile it, but then I kind of like can only see that yes, like the code I compiled is this, but it's like trying to profile JavaScript without source maps or trying to profile Rust without dwarf information, right? Like you can see the assembly that it's running, but you need to be really understand your own code and really be good at essentially reverse engineering to figure out then what's happening if you don't know why that code was emitted essentially. And so do I have another slide now? Yeah, so like kind of like the solution here, which I have a prototype, but it's not finished essentially. It would be neat to have a fairly like lightweight library that allows you to generate WebAssembly, but at the same time also annotated with dwarf information. Because this is, like oftentimes, essentially, at least for this kind of like my use case, right? Like it's a simple language. We're not doing too many optimizations, and ideally we just want to be able to emit WebAssembly as fast as possible, and if needed, also add dwarf information and debug information so that the profiler can then, return, yeah, you spend time in this specific line of code in your source code, not in the emitted code. And yeah, so I guess that's another thing that we need to see happening. And with that, I've finished my talk, which I guess is a bit early, but I guess it's more time to get refreshments and also questions.